Hi, I'm Owen. In this lesson, we'll lay out the fundamental components of the Kubernetes operating philosophy. To understand how Kubernetes works, there are two related concepts you need to understand. The first is the Kubernetes object model. Each thing Kubernetes manages is represented by an object, and you can view and change these objects' attributes and state. The second is the principle of declarative management. Kubernetes expects you to tell it what you want the state of the objects under its management to be, and it will work to bring that state into being and keep it there. How does it do that? By means of its so-called watch loop. Formally, a Kubernetes object is defined as a persistent entity that represents the state of something running in a cluster, its desired state and its current state. Various kinds of objects represent containerized applications, the resources that are available to them, and the policies that affect their behavior. Kubernetes objects have two important elements. You give Kubernetes an object spec for each object you want to create. With this spec, you define the desired state of the object by providing the characteristics that you want. The object status is simply the current state of the object provided by the Kubernetes control plane. By the way, we use the term Kubernetes control plane to refer to the various system processes that collaborate to make a Kubernetes cluster work. You'll learn more about these processes later in this module. Each object is of a certain type, or kind, as Kubernetes calls them. Pods are the basic building block of the standard Kubernetes module, and they are the smallest deployable Kubernetes object. You may be surprised to hear me say that. Maybe you're expecting me to say the smallest Kubernetes object is the container. Not so. Every running container in a Kubernetes system is a pod. A pod embodies the environment where containers live, and that environment can accommodate one or more containers. If there is more than one container in a pod, they are tightly coupled and they share resources, including networking and storage. Kubernetes assigns each pod a unique IP address. Every container within a pod shares the network namespace, including IP address and network ports. Containers within the same pod can communicate through localhost 127.0.0.1. A pod can also specify a set of storage volumes to be shared amongst its containers. By the way, later in the specialization, you'll learn how pods can share storage with one another and not just with a single pod. Let's consider a simple example where you want 3 instances of the Nginx web server, each in its own container, running all the time. How is this achieved in Kubernetes? Remember that Kubernetes embodies the principle of declarative management. You declare some objects to represent those Nginx containers. What kind of object? Perhaps pods. Now it is Kubernetes' job to launch those pods and keep them in existence. But be careful, pods are not self-healing. If we want to keep all our Nginx web servers not just in existence, but also working together as a team, we might want to ask for them using a more sophisticated kind of object. We'll tell you more about this later in the module. Let's suppose we have given Kubernetes a desired state that consists of 3 Nginx pods, always kept running. We did this by telling Kubernetes to create and maintain one or more objects that represent them. Now Kubernetes compares the desired state to its current state. Let's imagine that our declaration of 3 Nginx containers is completely new. The current state does not match the desired state. So Kubernetes, specifically its control plane, will remedy the situation. Because the number of desired pods running for the object we declared is 3, and 0 are presently running, 3 will be launched. And the Kubernetes control plane will continuously monitor the state of the cluster, endlessly comparing reality to what has been declared and remedying the state as needed.